Okay, so hopefully this will be recording, okay? So, all right, so yesterday we did the basic derivation for the principle of virtual work, and we did two problems, okay? So today I'm gonna define what is known as, or what I like to define as the internal virtual work. Okay, so over here, just write down, let us assume a uniform beam, okay? And let's say it doesn't matter what type of loading you put, but let's say the classic one for will be bending with a force P. And now, let's say we make a cut to that beam. Okay, so this is internal. The term internal, I'm referring to internal actions that happen within the beam. Okay, so over here now I come, if I take that element over here, which is at the cut, then due to the external load, what's gonna happen here, you're gonna have some stress, okay? And you know the general definition of stress is F over A, where A over here is simply the cross-section of the beam. Okay? So, I mean, this is very simple. So from here, what do you get? We get that the force will be equal to the stress times the area. Okay, similarly, if I define here the strain, what is the strain? The definition of the strain is the elongation divided by the initial length. Okay, or in mathematics, this is just that how much is going to elongate divided by the initial length. And let's say that this is more or less proportional to the elongation, let me call it delta. So will be basically the elongation will be our virtual deformation, okay? And that the initial length will be the width of our element, ds. So if I redo here a little figure, this will be the ds, the initial length, and the virtual elongation here will be our virtual deformation. Okay, I just changed the notation. You could leave it with the same notation, but I just decided to change it. So then from this equation here, we're gonna get that the elongation, So from this equation, the elongation will be equal to the strain times the initial length ds. Okay, so why am I doing all this stuff? It's because now with these two equations, we're going to be able to substitute them into the equation of virtual work, okay? So recalling the virtual work equation, which is what? Partial virtual work is equal to 0, okay? And what is work? When I did the division, what was the work? Remember we had here, work is forces times distance, no? So if I do multiple forces, will be integral of forces ds. Okay? Where this is W the work. So I could just rewrite this as, I did the opposite on the yesterday on the derivation, so it will be summation of forces, d of virtual delta s. I did the opposite, I went from here to here, okay, yesterday. So wait, this is equal to 0, this is equal to 0, let's not forget that. All right, so now, if I say, what is the value of our force? I mean, that we just calculate on top. The force will be equal to the stress times the area and then our DDS here will be equal to what? Will be equal to delta epsilon, that way I don't have to substitute both of them, ds equal to 0. So I hope you see what I did here. Just substitute this one by the epsilon ds, but I just put the sign to this one because really they mean the same, no? So you're not going to put delta of ds, no? So I kept the ds unchanged, but I just put the little change on the deformation. That is really the strain. What is really the strain? The strain is a deformation, no? Okay, so I just put it there. But again, this is a deviation, is not that important. Okay, so I'm gonna have to go to the next page. Almost done. Okay, so let me just rewrite the same equation. Okay. So now, okay. So this is from previous page. All right, so now I'm going to write this just a little bit differently. So this will be equal to the integral of the stress, virtual strain, which is a deformation. And then what I'm going to put over here is the two terms A, BS together. So what would be ADS? If you multiply the area by the length, what are you going to get? You get the volume. So really this is equal to differential volume, no? Okay. So over here, you're going to have that equal to stress, partial strain, dV, where V over here is volume. So now let's go back to the fundamentals. This is work, correct? So what is work? Force times distance. You agree that the stress is related to the force, no? Okay? And that the strain is related to the deformation, no? So really this is the same thing, okay? Or I'm just going to rewrite it, or it can be written as what? So we call this virtual work, but since we call it internal virtual work, I'm just going to put virtual work internal. In this case, will be equal to what? Stress times the virtual strain, which is a deformation, dV. Okay, and this will be the expression for the internal virtual work. Okay, when I told you that this is the power tool for structure, this is true. I mean, we're not going to go into detail, but all the finite element programs are derived from this. So I'm trying to pause this, but I'm not showing up this one here on top. Okay, so just like I was saying, that this is extremely powerful, even though we're not going to go through the basic derivation and everything, but this equation here is what is behind the finite element method. Okay, what you do in finite element is that you assume a deformation, and what you do is that you determine for the structure all the different case. Remember, like we did yesterday, with all these different, you can model this under this form of structure. So with the finite element, what it will do is determine the different case at each one of the nodes on the mesh. It will define the different case, no? So you can find the deformation. But again, this class is not a finite element, but to tell you that the fundamental behind it is this equation here, okay? Okay, so now, a more general form for the principle of virtual work is given by, so basically the equation we had was this one at the beginning, at the start. So now let's just say we can write this one as, we can break this component into two. We're gonna have internal virtual work plus external virtual work. And this must be equal to 0, okay? So the external will be pretty simple. We always be what we just defined will be the force times the virtual displacement, okay? So if you want, where in this equation you will have theta, and for the external, let's see what notation I can use so I don't confuse. Okay, so and for the external, basically will be just the whatever will be the amount of forces that you have. Let's call them S sub I times the virtual deformation that we have been calling Q sub I, okay? So it's force times deformation, where N would be the number of forces. Okay, so I give you the general now notation, and this will be the external forces. The S sub I will be the external forces. The stress this one will depend on the type of loading on the structure. But if I give the general expression, you can have axial load, and you can have bending. Okay, and this is a simplification for a symmetric cross section, okay? So depending on what type of loading stress the structure will be subjected, you would take one component, the P over A, or you will take the bending, or you will take both of them, or you will just take one. And then the strain, this term over here, you will get it from where? From the Hooke's law. This is equal to E epsilon. So you have here that your epsilon will just be equal to the stress divided by the Young's modulus. Young's modulus, but is generally known as the modulus of elasticity, okay? All right, so now I'm gonna define one more thing, and then we're gonna start working on specific cases. Okay, so this equation here personally is the one I like to use, but people don't like the term virtual work. They kind of get scared about it. However, if you tell the term energy, everybody likes it because they think everything is easier, but it's actually exactly the same thing. Okay? So now what I'm going to define is something known as the strain energy. Okay, the only thing I'm going to tell you is that for me, there's no such thing as something called potential energy. Okay, remember you had from your previous classes, you had something, the kinetic energy is what? 1/2 mv squared, no? Final mass initial. Now, what is the potential energy? For gravitational force, the potential energy is equal to what? mgh, no? Okay, why do they call that potential energy? I mean, I know why, okay, but really, what is the definition of work? Force times distance, correct? What is the value of the gravitational force? What is the expression for the gravitational force? mg, correct? And now, what would be the distance that is moving? h. So really, there is no such thing as potential energy. It's really work done by the gravitational force. Similarly, what is the other potential energy you're used to is the one of the spring, 1/2 kx squared. All right? So what is work? Force times distance. What is, so integral of force. What is the force of a spring? Kx. What would be the deformation? Dx. If you integrate kx dx, what do you get? 1/2 kx squared. Okay? So this is what they call here strain energy is really potential, is really, I mean, I don't like to call it this way, but it will be some type of potential energy due to strain. But really for me, it should be called work done by the strain, which is what the expression we just derived shows, no? Force times deformation, okay? All right, so I'm not gonna do the derivation, even though it's pretty simple, but I don't think it's gonna add anything, but it can be shown that the virtual work done by internal forces, which in our case will be the stress, can be rewritten as the following. So you have stress times strain dV, and this is going to be equal to 1/2 dV. Okay, and without doing the derivation, if you want, I can give you, no, I'm not, I can give you a little hint, but again, is what's behind the idea. What would be the derivative? What is the derivative of d sigma square? D epsilon square will be 2 epsilon d sigma, no? So really, E epsilon square could be written like 1/2 of this term, okay? It's really what it's based on, but I'm not gonna do it here because it doesn't add much, okay? But the idea is behind is using what is the derivative of something called is 2 epsilon d epsilon, okay? All right, so with this term over here is what is known as the strain energy. And I can rewrite it differently as well, okay? So let's say, I have here, so strain energy generally is defined with the letter U is equal to, oops, 1/2 of this is generally the way it's expressed, but maybe this will give you a hint about how it's derived. I don't have this one on the notes, but I give it to you. if you use the expression Hooke's law, okay, what would be the stress equal to? Would be equal to E E times E epsilon, so it would be E epsilon squared dV, no? And maybe here you see where is this half coming? Because if you take the derivative, you will get the 2 over here, so you need to divide by 1/2, no? To get the same thing. But generally, the way is known is on the first form. Because in here, yes, you can see more the term strain, but in here you can see clearly that this is force times deformation, okay? While in this one, you just see that everything is in function of the strain. That's why they call it strain energy, okay? But this is the most common form here. And again, this is extremely useful and powerful, as we will see in a little bit, okay? So using this. So now we're gonna do, and this isn't the important part now to understand. Before was just derivation, but this part is important because that's what you will have to be doing over and over. So strain, energy, due to, I call it in-plane, but let me just call it here axial loading because it's short to write it down, and it's the same. Okay, so imagine here you need to study a structure that is subjected to an axial strain. So again, let's take a simple structure. Let's take a beam. And what is axial loading? Force being applied on the axial direction, no? Of the cross section. All right? Again, here. Okay, I'm not gonna. So for this case, for axial loading case, what is the expression for the stress? Before I told you that this will be the full expression, no? But if there is no bending, we only have the first term, no? Axial. So will be axial will be equal to P over A, where you know that A is just the cross section of the beam. Okay, so we know this, and what I did over here, and using, I mean, the same thing that I say over here on the previous page. Now, how do we find the strain? By using Hooke's law, okay? So, and using Hooke's law, which is what? Stress equal to Young modulus times strain. We're gonna have that the strain is equal to stress over E. Sorry for that, it should be an E over here, which is equal to P over A divided by A. I'm going to the next page, otherwise I'm going to be putting too much. So page 75. So now what I'm going to do is substitute into strain energy equation, which is what? U equal to 1/2 stress of force given by the stress times the strain times dV. So what is the stress equal to? We have it on top. It's equal to P over A. What is the strain equal to? P over A over E. And now we have here dV. Okay? All right, so we do some simple algebra. Here, this is going to give us is equal to 1/2 integral of P squared over EA squared. And now to save one step, what is dV equal to here? dV, we said before, is equal to A times ds if you want. Well, what is ds? This is when you do the beam. Okay? If you multiply the area by the length, you get the volume, no? So that means I can just rewrite this as A ds. So finally, what I'm going to get is that the strain energy when a structure is only subjected to in-plane loading is equal to 1/2 integral of P squared over EA ds. And this term over here will be the strain energy due to axial loading, or sometimes it's called in-plane loading, okay? It's within the plane. So did you follow the procedure, what we did? Okay, it looks pretty simple. So this is why it's important. So now, imagine that now we're gonna assume a structure which is subjected just to bending. So now, second part will be strain energy due to bending. Okay, so if I follow exactly the same steps that I did before, this time let's assume, okay, it can be a force, but since we just call a bending moment, let's just assume a moment over here. Let's say it's bending upwards, so we'll have a moment, no? Okay, M. So follow exactly the same steps that I did before. So for bending moment case, what would be the value of the stress? So if it's only bending in one direction, we just have the expression my over I, no? We have here my over I. Okay, and similarly, I'm going to say here, I'm just rewriting the same thing and using Hooke's law, which is sigma equal E epsilon. We're going to have that the strain epsilon equal to stress over Young's modulus. So this will be equal to my divided by EI. I mean, so far, the only relation you need to know is which one? This one, no? And then depending on the type of loading, you should be able to derive this expression. So I don't ask you to memorize this one. I want you to be able to rederive them. It only take about 3-4 lines. Here, the same thing. So what is the next step? Now we're going to substitute into the strain energy relation, the same thing we did at the top. So substituting. Substitute into strain energy equation, U equal 1/2 force given by stress deformation given by the strain dV. What do we have? What is the expression for the stress? Y over I. What is the expression for the strain? We have it right on top. Is Y over EI dV. So now, just some basic algebra. This is equal to 1/2 of m squared over E I squared times y squared and if you remember what was dV, ADS, no? So I can write this as y squared A ds. Okay. And now, okay, let's put it here. Recalling that, what is the definition for the moment of inertia? Is integral of y squared dA, no? So we can say that y squared A, this term over here, will be equal to what? Will be equal to the moment of inertia. Okay? So if I do that, we have that U is equal to 1/2 integral of m squared over EI times, so this term over here is I, okay, after integration, no? You integrate this, same as this, no? 1 squared A, so this is times I times ds. So at the end we have, where did I write it on the previous page? Okay, so finally what we're gonna have here is that the strain energy is equal to 1/2 integral of m squared. Oops, I forgot something here. I forgot the square over here. So 1 m squared over EI ds. And this will be the expression for the strain energy due to what type of loading? Bending. Okay, so today's class is a lot of theory, but do you follow the process in order to do this? It's not complicated, no? Okay, so now we did axial, we did bending. Next thing we need to do is maybe torsion, no? The other type of loading we have. So let's see what would be the strain energy due to torsion. So again, I'm going to follow exactly the same steps. Let us assume it's simple beam. And in here, I mean, there's two ways to do the notation, but I think one is a bit confusing. Let's say this is, we do the torque around the x-axis, no? So I think it's, I don't know if you have seen that notation, but I think it's easier for figures. It would be a torque. The double arrow means that it goes around the axis, no? Okay. So it's subjected to a torque. So, okay, so in the case, no, in the pure torsion case, we're talking a bit yesterday about it. What is the stress? They changed the notation. Instead of sigma, they use tau, but you could use sigma because it's still stress. So tau was equal to what for torsion? We say was equal to T times R divided by J, where J is the modulus of rigidity for torsion. So this is equivalent to the E, but for torsion, no? Resistance to torsion. Okay. And now, and using Hooke's law, for torsion, so what is equivalent to sigma equal E epsilon for torsion? Is tau equal to what? G times what? Gamma which is the angle that it deforms, okay? So this is equivalent to the sigma equal E epsilon. All right. So, and in that case, I think what did I do? I think I did it for the other one. So in that case here, you're gonna have that the gamma when it is, that the gamma will be equal to the tau over G will be equal to TR over GJ. Okay. So the next step is to do what? Substitute into the strain energy relation. Substitute into strain energy equation, which again is what? Is U equal to 1/2 integral of sigma epsilon dV. So in our case, this should be equivalent to what? What is the stress for us? Is tau for shear stress. The strain will be given by what? By the gamma. And we still have the dV. Okay, so this will give you what? Do as before, 1/2 integral of stress was given by TR over J, okay, from the previous page. All right, and this one, gamma would be TR over GJ. So we have now times TR over GJ dV. Okay, so now I need to do a little figure to go to the next step. So generally torsion will be in a circular cross section. Doesn't have to be, but after we do the division, I'm going to ask you something. But let's say you have something circular this way. So in order to calculate the volume, you can have, let's say this will be ds, will be you go around the circumference. Let's say this has a thickness T. And a length dx. Maybe I should keep this one. Yeah, it's fine. Too late to change the notation. So if we do this, what would be the volume of this tube over here? What would be the area? T ds, no? The circumferential area. And now you need to multiply this by the length, so it will be times dx. Or you could just say that dV is just equal to what? A dx. Okay, so now if I use that information to rewrite the strain energy is equal to 1/2 integral of, let me see, I can rewrite this, T squared over G J squared. But now I'm going to write over here the top one as R squared A dx. Okay, same as before. And recalling that J is also a moment of inertia. But for torsion, and it's equal to what? It's equal to R squared dA, which really means that this term over here is J. So same as before. So at the end, so that we have what? The strain energy will be given by what? 1/2 integral of T squared divided by Gj times dx. And this is the same thing as the moment. What was the previous expression? M squared divided by EI, no? So the T is equivalent to the M, the G is equivalent to the E, and the J is equivalent to the I, no? Yeah, for torsion. So really it's the same expression. So this one will be the strain energy relation due to torsion. Okay, so we have one more, which what we have been studying all the time, is that we have been studying shear flow, no? Okay, so now is to know what is the strain energy due to shear flows, and that will be the last one. Okay, so here imagine that you have a cross section. I mean, I don't make it circular, it can be anything you want. But in here you can have a shear going across the cross section, no? Or the same as we did, some of these ones here, the this type of cross section. Okay, which would be the case. You can have shear going this way, this way, this way, and this way. Okay, whatever you want. This could be the shear as well, if we do a figure. Okay, so here I'm going to go a bit faster. So we know that the strain energy, the general equation, U is equal to 1/2 stress times strain times dV. But for shear, on the previous case, we just rewrote this one as being equal to 1/2 integral of what? For shear, you need to replace the sigma by the tau, the strain by the gamma, and you can leave the dV. All right, so this one is a bit more complicated, not because of the mathematics, it's identical, just because you are not as familiar with the shear flow as you are with axial and bending or torsion. But basically, what do we have? Recalling that, what are the units for shear? Shear is force per unit length, no? So really, what is also known is equal to the shear times the thickness of the whatever cross section you are using. So if this will be force meter square, no, newtons meter square. If you multiply by meters, you will have newtons per meter. Okay? So this one will just tell you then that the tau, the shear stress, is equal to the shear flow divided by the thickness. Okay? And now, I'm not going to do it again, but what would be the Hooke's law for shear? Is tau equal to G gamma. So this will give you that gamma is equal to tau over G, which will be equal to Q over GT. All right, so again, we go and substitute. Into strain energy equation. So U equal to 1/2 tau gamma dV will give us what? 1/2 integral of tau is equal to Q over T times Q over GT dV. And as before, what will be the volume equal to? TDS dx, which will be equal to, we can leave it this way here, okay? You don't need to put the A because we need to eliminate the T's. So you leave it under this form. Okay, so this will give us what? 1/2 integral of Q squared over G T squared times T. Oh, I wanted to do, okay. Wrong color. I wanted to do it green. So let's see. T ds dx. So we see here we can cancel one of the T's. So now be careful because I'm going to rewrite this a little bit differently. So it's equal to 1/2. This is the double integral, so you need to integrate first between 0 and L. That would be the length of your beam, no? Okay, or your bar. But now your ds here, that means that you need to do the calculations or the shear flows around the cross section, no? Okay, and we can call this one ds. So that would be another integral. So this will be equal now to, let's see, integral around the cross section until you close it of Q squared over GT ds. And then you need to multiply this by dx, which is the length of your beam. So finally, this is the strain energy due to shear flow, Q. The previous page, 77. That one? I mean, it's basically exactly the same procedure. Okay, guys, so here we are. Let's do a little summary of all those expressions. Summary of strain energies. So which one do we have? We had the axial, and if you pay attention, they all basically look the same thing. What do we have? U was equal to what? 1/2 P squared over EA. Because what is resisting the in-plane load will be the cross-sectional area, no? Will be resisting the in-plane load, and this was ds along the length. Second case. Bending. This time, what is the loading? Is the bending moment, so m squared, before was p, now it's m squared. E is because you need to define the material. Now, what is resisting the bending? Is not the area anymore, but the moment of inertia. And it will be again ds. Third one, torsion. What is the loading? The torque, T. Now, G is related to the material, to resist to the material, and J is related to resist the torsion. And again, then we had ds. Did we have ds or dx here on this one? I think we had dx, no? I changed the notation. I think it's, yeah, dx. So put here x. dx. And then the last one was shear flow, which is the most complex one. U is equal to 1/2 integral along the length of the beam, but then you need to integrate around the cross section, Q square divided by GT. So this is ds, and the outside is dx. Okay, I'm going to stop this video over here. If that stuff lets me, because I don't know how to get the stuff on top.